Hi, my name is Nick. I'm a scientist at AER, and today I'm going to be discussing the use of CRIS ammonia observations to improve emissions estimates of ammonia, and then ultimately with the goal of improving decision making on PM 2.5. So this is a collaborative effort across many divisions at AER, along with colleagues from Environment and Climate Change Canada, and a lot of help from the folks at the EPA. So we're very grateful for them. All right, so the overall project goal is to use CRIS ammonia observations in a finite difference mass balance inversion to improve emissions estimates of ammonia and then provide those emissions to you all, the air quality modeling community, to hopefully improve decision making on PM 2.5. This was motivated by the fact that we can identify NH3 sources and improve estimates of NH3 emissions using observations from space from the Cross-Track Infrared Sounder, or CRIS. So as an example of this, the plot on the right here is showing the warm season surface average concentration, so from April to September of 2013, and then the corresponding AMON surface network observations for that same period. And so what we generally see is that CRIS gets things, is showing very similar concentrations. We see, high concentrations where AMON's sensing high concentrations. We see some of these gradients to lower concentrations. But the key here is that we see a lot more information than we get from the ground sites, because we can see extended areas of higher concentrations. We can see regions of high concentrations where there isn't a sampler nearby that we wouldn't detect this. And so we get a lot of valuable information from CRIS. And so the goal is to take that information and try to make it useful for air quality modeling. So here's kind of a schematic overview of how we're trying to do this. So all of it is being done on Amazon Web Services, and it begins with our AQCast preprocessors, where we're running WRF and all of the preprocessors for CMAC. We run a couple versions of CMAC, a baseline and then perturbed, where we perturb the emissions of ammonia. And then the results go into this emission scaling factor calculation, which is where the CRIS retrievals come in. And then that updates the final ammonia emissions, which then we run in a CMAC optimized version. And then we can iterate over this loop toward a convergence of the final emissions. Once we get that final CMAC optimized, we want to compare with independent data, so things like the surface network from AMON, or if it's available, aircraft data. And then once we're happy with the emissions, the final goal is to have it basically go into this system where you all, the end user, can go in, request the data you want, and then this would all happen behind the scenes, and you would just get provided with model-ready files. So today I'm going to be discussing mainly this loop here, where we're actually doing the running the CMAC and calculating the emission scaling, and then comparing with observations. So to do this, so one of the unique things about how we're doing this is that we're applying it with the ammonia bidirectional flux, and because we're doing that, it requires a couple extra simulations, so it ends up being 4 CMAC runs per iteration. And this is just kind of a quick schematic of how we're doing it. So it starts with the CMAC baseline, then we run a perturbation to the input into the bidirectional flux, which comes from FESC. Then we run a perturbation to all the other ammonia emissions. We calculate this beta, which I'll discuss in a minute, which then allows us to calculate the final emission scaling factor. Once we have those final scaling factors, we plug them in, we run a final optimized CMAC, and then the process can start all over. So now I just want to quickly walk through each of these steps so you can see how we're doing it, and then finally get you to some results. So the first step is to perturb the FESC inputs. So the variable we're perturbing is the 0 to 1 centimeter ammonia, or L1NH3, and we're increasing this by 20%. And this is with a lot of help from folks at EPA, trying to figure out what's the best variable to perturb if we're going to modify the inputs to the bidirectional flux scheme. So we make that simulation, then we perturb all the other ammonia emissions by 20%, so everything else from the processing done in smoke from the NEI data set. Then, having two separate perturbed runs and the baseline, we can calculate this beta for each perturbation. So what beta basically is it's just a sensitivity of the simulated surface concentration to these emissions perturbations we're making. So here in this equation, seeing what beta is, it's basically looking at how this change in emissions impacts the change in surface concentrations. It has a limit of 0.1 to 10, and this is basically just to prevent any one iteration of the inversion from going crazy in one direction, whether it's increasing emissions significantly or decreasing emissions significantly. And I just want to point out here that the beta is calculated separately for each perturbation. So for each run, we do this difference. This term will always be the same, but this will be different based on how the emissions perturbation impacted surface concentrations, whether it was the bidirectional perturbation or the all other perturbation. All right, with that, then we can calculate the final weighted emission scaling factor. And this is where we start to see a lot more terms, but it's actually pretty straightforward. And this is where we had to also add in an extra term based on this idea of using two separate perturbations. So in the standard mass balance finite difference approach, we have this basically the final emissions is equal to the a priori emissions times 1 plus this difference term, which is basically the observations from Chris minus the baseline CMAC divided by the baseline here, and then multiplied by this beta factor. What we changed here is we added this scaling term for either the bidirectional or for the all other. And basically what this is just weighting the final emissions or this whole scaling factor by the original ratio of either the bidirectional to the total or the all other to the total. And we had to do this because these betas, this whole process would be assuming that the entire difference between the observations in the model are completely due to this one emission source, but we know there's two emission sources, right? There's from the bidirectional and then from the all other. And so we're just simply making the assumption that the ratio would remain the same even after the scaling. So we're assuming the ratio is correct, and whether or not that's right or not is up for debate, I guess. But it seemed like a reasonable compromise with the data available to us. Again, we are putting limits on this from 0 to 5 just to ensure that things don't go too haywire on any one iteration. Once we have that final optimized CMAC, we can plug it back in and go through the loop again. So let's jump straight into the results now. So this is we ran this approach for June 2015, the WRF version 3.8, and so this was a WRF we had run for a different project that we're able to use here. From last year's CMAS presentation, we have updated to CMAC version 5.3.2. We're running the CONUS 12US2 domain, CB6R3 chemical mechanism, and we're using the NEI 2011 emissions. All right, so here is the results for the surface ammonia concentration. So on the left, this is the CRIS monthly average, and then on the right, this is the CMAC base monthly averaged. And then the bottom is just a simple difference plot showing CMAC minus CRIS. So where there's red, we see CMAC as over predicting, and blue is under prediction. So some things to kind of notice, it's kind of a mixed bag of over and under prediction. Over the southeast, we see we're over predicting. We see in this hot spot over the center of the United States, we're under predicting. And then kind of, again, a mix over the western half of the country. When we ran the inversion, this is what the final scaling factors looked like. So this is after calculating the betas and after applying the weighting. These were the final factors that were then multiplied by the a priori emission set. This is just one example for one portion of the BiDi input on the left, and then on the right for all other NH3 sources. And so, as we might expect, we see blue over the southeast, showing basically a reduction in emissions, and then we see warm colors over the center of the country showing an increase in emissions, and then kind of, again, a mix of increases and decreases throughout the other regions of the country. So going back to these were the initial results. Let's see how it looked after the inversion. So I'll just kind of go back and forth a couple times. So lots of things to point out here. The big one is if you just look at the difference plot in the bottom, you see that the reds become less red and the blues become less blue, indicating that things are moving in the right direction. So that's a good sign that the inversion is working correctly. If you look at just the spatial plots themselves, you see that qualitatively things get a lot better. For example, in the center of the country here, this hotspot looks much closer to observations after just one iteration. Over the southeast, we see a major improvement. So again, some of these hotspots that aren't showing up at all for CRIS, when we run the inversion, we see improvements. And then same with over California, and then in the Pacific Northwest, we see reductions over California and then increases in the Pacific Northwest. Again, matching much better with the CRIS observation. So at first glance, it seems like using the inversion with the bidirectional flux is working correctly. Of course, the next step would be to do this several times to get the final emissions estimates. But for now, we just want to look at what does one iteration do when we compare it to independent data sets of ammonia observations. So here what we're showing is the baseline comparison with the AMON network. So on the left is a difference plot at each AMON station, just showing the difference between CMAC and the AMON observation. So red meaning over prediction, blue meaning under prediction. And then on the right is a scatter plot so we can get the correlation. Basically, we see a correlation of about 0.66, and then if you look at these plots, we see similar trends to what we saw in the CRIS comparisons, with kind of over prediction in the southeast, some over prediction in California, and then kind of a mix and under prediction in some of the regions in the center of the country. After the inversion, we see the correlation improves to 0.7. And then we see that most of the dots, the comparisons at the AMON surface networks, move in the correct direction. We see it, for example, over the southeast, the dots become less red. And then we see some flips in some places, for example, in California, where it was over predicting, now it's under predicting. So kind of a mix of improvements and the inversion pushing emissions too far in the wrong direction. So in theory, this is where the multiple iterations would correct some of this and kind of converge on hopefully what is the optimized emissions. But nonetheless, encouraging to see improvements with independent data sets. So to quickly summarize, the goal of this work is to improve NH3 emissions using satellite observations, and then provide those emissions to you all, the air quality modeling community. The prototype application that used the bidirectional flux for June 2015 proved successful, and it even improved independent comparisons with AMON. And so right now what we're working on is kind of polishing everything up on the AWS side, automating everything, and then also making it easier for us to transition to different domains, which we've run into some roadblocks with that, but we're working on that. And so hopefully soon we'll have a final way for you all to request data and receive it. So that's all I have. I appreciate you taking the time to listen to this, and I look forward to your questions.